Hello everyone, this is Surya Nandu. I am pursuing BTech second year in VVIT College in the stream of ECE. Today I am explain about counters in switching theory logic circuit. Counter is a interesting topic in this subject, and this is the important topic in this subject. Counters is majorly used in electronic devices. Let us see the definition of counter. Basic definition of counter is a sequential logic circuit which counts the input clock pulse. We see the counters in our daily lives as an example. Clock is the one type of counter, and we see the another example. Counters are used at thermal plants to measure temperature in thermal plant. Counter is worked as it takes the signals and counts the changes in the temperature or in that surroundings. Counter is represented like this. It takes input as a signal is called clock pulse. Clock pulse has ups and downs and certain period, and it has a frequency. Is developed or implemented by a flip-flops. We require n number of flip-flops to develop a counter. If we take n number of flip-flops, the bits are n number of bits in that binary counter. The bits are taken from 0 to power n minus 1 bits. Let us see let us assume we take 4 bit flip flop. It has 0 to 16 bits. 0 to 15 bits we required. It is represented as 0 to power 4 minus 1. 2 power 4 is 16. 16 minus 1 is 15. We require 16 bits for 4-bit flip-flop. Bits are represented like this: 0 to 15, 0, 1, 2, 3, 4, 5, 6, and so on, 14 and 15. We take 4-bit 4-bit flip-flop. We have 4 bits in the numbers. We write bits 0 to 15. This is known as binary up counter. We write 15 to 0 like 15, 14, 13, 12 up to 0. This is known as the binary down counter. Classified into two types. They are synchronous counter and asynchronous counter. These counters are classified. Classification is based on clock pulse is applied on flip flops. Counters are two types classified. First, we see synchronous counters. Synchronous counters are designed very complexly, and these are high reactive and accurate accurate to counting, making them suitable to high speed application. Synchronous counters can be designed to operate any desired count sequences. Advantages is highly reactive and high speed applications. Disadvantages of synchronous counter is complex to design and high power consume. We see asynchronous counters. These are easy to we see the asynchronous counters. This has propagation delay due to operation in flip-flops. These counters are designed only fixed sequence of counter. These flip these flip-flops worked at a toggle state. Now we see the advantages of asynchronous counter. Asynchronous Asynchronous counters are simple to design or simple to implement a logic circuit or characteristic equation. Requires fewer logic gates compared to synchronous counter. Suitable for low speed applications where minimal hardware is desired. See the applications of counters. Counters are widely used in digital electronics, microcontrollers, and computers for tasks such as timing, frequency measurement, and event count. As we know, counters are classified into two types. They are synchronous and asynchronous. The synchronous and asynchronous counters are again classified into two types. They are truncated and non-truncated counters. These counters are class- classified based on the count value or mod value. Mod value is represented as mod value equals to n less than or equals to 2 power n, where n is the number of flip-flops in the counter. Mod n equals to 2 power n non-truncated. The counter is non-truncated. Mod n is less than 2 power n. The counter is truncated. Mod value is also known as is state. As mod value is given, we find the number of flip-flops required. State and number of flip-flops required is accurately equal, and based on mod value or truncated and non-truncated flip-flops, the flip-flop counters is again classified into three types based on the counting style: up counters, down counters, and up down counters. Counters are act as frequency devices. The input frequency of counter is F. Then the output frequency of counter is input frequency divided by the count value or mod value. As we see the synchronous counters and asynchronous counter and truncated, non-truncated, up and up down counters. Now we solve the one problem on example to design the synchronous up counter with the mod value A by using KJ flip-flops or JK flip-flops. Design of synchronous counter is six-step process. The step one is finding number of flip-flops required for design. Number of flip-flops required is finded by the relation mod value n less than or equals to 2 power n. Here mod value is given 8. Mod value is less than or equals to 2 power 3 where n is equal to 3. 8 is equal to 2 power 3. 8 is equal to 8. Therefore, number of flip-flops required is 3. Next step is implement state diagram of the counter. State diagram is represented any shape and state is represented with circle and state transition is represented with arrow. We in the 8-bit 8-bit synchronous counter we have 8 bits 8 states. This is the state diagram of 8-bit synchronous counter. Next step is implement state table from the step 2. This is the state table we draw from the step 2. We have 8 states in the 8-bit synchronous counter. We have 3 flip-flops. State 0th state. The next state is 1. First state. It has next state is 2. Like this. We write like this. This is the up counter. As we discussed 0 to 2 power n minus 1. These states are represented like this 0 to 2 power n minus 1. 2 power 3 minus 1, 8 minus 1, that is 7. 0 to 7 states we require or we have. Next step, fourth step is implemented the excitation table of counter. Our 8-bit synchronous counter is designed with JK flip-flop or KJ flip-flop. We prepare the excitation table for JK or KJ flip-flop. This is the excitation table for KJ flip-flop. Now we see the present state and next state. This has in A flip-flop, present state is 0 and next state is next step is implement or implement simplified expressions of flip-flop inputs in terms of present state of the counter. These are simplified expressions from the step 4 in excitation table. These are the simplified expressions. We use these expressions, we implement the logic circuit for 8-bit synchronous up counter using JK flip-flops. Next step is implementation of logic circuit diagram. This is the logic circuit diagram for 8-bit synchronous up counter. Thank you for watching.